Okay, so now we're talking about chapter 24, sections 5 through 8, more about electric potential and this relationship. So don't forget, in general, we've got, E is negative dV dr or dV dx, something like that. In a uniform electric field, E is negative delta V over delta x, something like that. So then rearranging and using the calculus, delta V, the change in voltage, so the change in electric potential, is negative integral from initial to final of E dot ds, right? Or it's negative of initial position final, E dot dx or something like that. Okay, so that's how we calculate electric potential from electric field. Here's how we get electric field from electric potential. Okay, and so the derivation there in 24.6 is showing how we get the potential due to a single point charge. Remember, potential we're thinking of as like this sheet that's sort of stretched out. Positives push up, negatives push down, and then at infinity is where the potential is zero, just like gravitational potential energy. And so the way we calculate this, it looks just like gravity, is kq over r. So remember, it was gm over r, or gmm over r. For this, it's kq over r because we're just talking about the potential per unit charge, right? The potential energy per charge. And so instead of kqq over r, it would be kq over r. That's the potential due to a single point charge. And again, that goes to zero as you get an infinite distance away from it. And so what does the shell theorem tell us? Outside a uniform spherical charge distribution, when little r is bigger than big R, then E is kq over r squared, so V is kq over r, right? Like we've seen before. And so we have this first example. Right, and in this example, we want to know the potential at B due to the other charges. Right, so there are two charges there. Q1 is negative 2 microcoulombs, Q2 is positive 3 microcoulombs, and B is 4 and 3 meters from each of those respectively. And so part A, V is K times the sum of Q over R. Right, I'm just adding up these things. So this is going to be 9 times 10 to the 9th, and then one of them is negative 2 times 10 to the negative 6 coulombs over, I think that's 4 meters, and the other is 3 times 10 to the negative 6th over 3 meters. And so you do that calculation, I think you get 4.5 times 10 to the third newtons meters per coulomb, or joules per coulomb, or volts, right? All those units mean the same thing. Newton meter is a joule per coulomb is a volt, all that kind of stuff. And then B is asking now, what is the work required to add another point charge there? Right. Well, let's think about this from the unit perspective for a second. I want work. Work is in what unit? Joules. No matter what unit we're in, what class, E&M, mechanics, work is always in terms of joules. Well, this is joules per coulomb, right? So if I take this number and I multiply it by something with coulombs, I get joules. And so work is going to be Q times V, charge times the voltage. And so to bring in 4 microcoulombs, so that's 4 times 10 to the negative 6 coulombs, times this, the 4.5 times 10 to the third, and there you get 18 times 10 to the negative third joules. And the idea there is we're taking this charge of 4 microcoulombs and we're bringing it in from infinity all the way to this point B. All right, so we're going from 0 to there. So it's Q delta V would be, from 0 to that point. Okay, and then you can see there the potential due to an electric dipole, how this gets calculated. And so we're adding up the charge from each of those, and that's just a formula that we get. You're not going to need to know how to do that particular derivation or anything. And so example 2, where does v equal 0? You know, remember here that v is a scalar, and so we're not asking about electric field. That's going to be different, right? So again, the way I would recommend doing this is thinking of this as a like a sheet that's stretched out, and positives push up in the sheet and negatives pull down in the sheet. So if I have two positive charges, right, plus 3, here it's like I've got these two things pointing out, and so everywhere it's going to be positive, right? The sheet is pushing up everywhere, and so this is nowhere. Only at infinity is the voltage 0. Okay. Same thing with the other one on the top, -3 or -6. These are indented down, so everywhere it's like the sheet is down below 0, and so again here only at infinity is that going to be the case, right? And so then here, if I've got -3 and +3, now here this one's pushing down in, this one's kind of pulling up, and so there would be a line right down the middle where it's 0, where the voltage is 0, right? And this looks like a plane going into the paper, right? Because even at different levels here, it'll be 0 anywhere along this plane that comes out of the board. And then this one, if I have +2 and -1, you can imagine, you know, this one is pushing out, that one's pushing in, and so what happens is this one is bigger than this one, so overall it looks positive, right? And so the place where it's 0 is going to look sort of like an egg shape going around the -1, because as you get farther away, you're going to reach the point where you've got positive potential, and then at some point here it's going to go negative as you get closer. Okay. And so again, we're not looking at electric field, because here electric field would be 0 right in the middle, but now it's nowhere, right? What the electric field is the derivative of this field, and so it does get flat, right? It does have 0 slope, you could think of here in the middle. And then here, even though the potential is 0, the electric field is not 0, because here the electric field points this way very strongly. So we need to keep those two things in mind, but we can think of them in terms of their calculus relationships, that E is the derivative of the voltage. Okay, and so take a look at the next example. It's example 3. Mine, the hole is right in that spot. And so, let's see. So for part A, you know, you've got 3 all around, and so what is V at the center of the square? Sorry, these are +3, these are -3. And so at the center it's going to be 0. Again, these are pushing up, these are pulling down, all with equal amount, and so you're going to end up with this 0 electric potential plane right through the middle, like that. Okay, and the same thing is going to be true also for part C. Part C, you're going to end up with the same thing, because you got -3, -3, +3, +3, and so here down the middle it's going to be 0, kind of vertically. Okay, so let's take a look at B. Do some calculations involved there. B, we've got -3, +3, +3, and +3. Again, keep in mind these are scalars, so it doesn't really matter exactly where they're located in relation to each other. All we know is that this one is going to cancel out with one of these. Those are going to sort of balance out, because they're all the same distance away from the center. Let me move something here, right? So if we're at this point here, that means I've got these two are the only ones that are really affecting it. And so that calculation will look like this. V is the sum of KQ over R. So I've got K, the net charge around, there are two of these, right? So 2 times 3 times 10 to the negative 6 over A, where A is the distance from the center to the corner. And so this ends up being 6 times 10 to the negative 6th K over A, where K is Coulomb's constant and A is that distance which we don't know. And then the unit, of course, is in volts. All right, so that's the answer to B. And then let's take a look at D. In D, again, we've got, this is negative 3, negative 6, negative 6, and plus 3. Or this is plus 3 also, right? Let me just check that. Yeah, okay. So then what's going to happen is, plus 3, negative 6, these all sort of cancel out. And what we're left with is this one then, adding up in a scalar kind of way. And I get the same thing as before, except now it's negative. So this is, V is the sum of KQ over R. So it's negative 6 times 10 to the negative 6th K over A. A is, again, is that distance, volts. So that is the electric potential at that point due to these charges. All right. So now getting into the calculus idea, conceptual calculus of electric field and how it's related to electric potential. And so for example 4, it says given V, find E for the intervals 0 to 3 centimeters, all these things. Recognize this is in centimeters. Actually, I hope it's in centimeters on your slide. I may have changed it from last year, but so what are we looking at here? Again, what's our relationship? The electric field is dV dx. X is our variable in this case, so we'll use x. And so I'm looking at the slope, right? So for part A, from 0 to 3, the slope is 0. So the electric field is 0. Part B, I'm looking at the slope there, and the slope is, it goes up, let's see, 3 in about 3 centimeters. So 3 volts in 0.03 meters. So that's about 100, negative, right, because it's the negative, sorry, I forgot that. Negative 100 volts per meter. Notice the units are in volts per meter. And then C, here we're going to look for the average ultimately, right, because here it goes up 2 volts, or 1 volt rather, in a space of 4 centimeters. All right, so that comes out to about negative 25 volts per meter. Okay, so again, the electric field is the negative slope of that graph. All right, that means then if I have a graph telling me the electric field, like in example 5, right, then the change in the voltage, find delta V, is going to be negative integral E dx, right? And so what I'm looking at here is the area under the graph. And so from 0 to 3 meters, hopefully it's changed in your thing. 0 to 3 meters, what's the area there? Well, it's 400 times 3 meters, right? 400 volts per meter times 3 meters. Notice how the units work. So this is 1200, be negative 1200 volts, right? And then for part B, again, what's the area there? I calculate about 1650. Again, all you're doing is just finding the area under that graph. It should be negative. And then C, going from 6 to 10, I think you should get about negative 3095 volts or something like that. So we get a total change of negative 5,925 volts. Right? And then the next part of this, in the next box, it says sketch V as a function of X. So what does that look like? Well, we're going to use these numbers to help us out. All right, so hang on to those. So if I have, so it'll be a negative graph, right? So here's V, here's X. We go all the way out to 10, so 2, 4, 6, 8, 10. And we can go down to about 6,000. So let's say this is 2, 4, 6, negative 6,000 volts. And so my first line was at 3. 3 was at about 1,200, right? So maybe about there. And that's going to be a straight line. How do I know this is a straight line? It's a constant line because in the E field graph, that's a flat slope, right? And so that means this will be a straight line. So it's a constant slope here. And then notice it's getting steeper, or it gets steeper, right? So that means the slope is increasing, but negatively. And then we get down to 6 is almost at about negative 4,000. So it's kind of going like this. Okay, so this is about negative 1,200. This is about negative 3,850, right, because we add that up from the other one. And then in total, by the end, right, we get down to 10. It's about here, close to about negative 6,000. And so this is flattening out a little bit, but it doesn't go all the way to 0. It's just going to go to, again, to some constant slope. Rather, it's still getting steeper, I should say. The slope is increasing there. But it's getting difficult to draw. Anyway, so that's what the graph is going to look like for the electric potential. Okay. Okay, and this next problem is from the textbook. It's number 20 from the homework packet, so this one's already done for you. But the idea here is we've got this graph. So here's some particle a distance d away, right? And then this particle we're moving along here. So this is, y, this is x, there's particle 1, particle 2. And then we've got this graph giving us the electric potential as a function of, it's the electric potential at the origin based on the location of this thing, right? And so we can see that when this is at 8 centimeters, that's when the electric potential is 0. So at 8 centimeters, that's where these two have the same potential. And so the question is, first of all, is this positive or negative? Well, notice when this thing is at infinity, when it's an infinite distance away, then I have positive potential. So that means I know that this is a positive charge, right? And then notice it says that the electric field, or rather it has an asymptote, right? This has an asymptote of 5.76 times 10 to the negative 7th volts. That means that when this is an infinite distance away, the electric potential here is this, right? So that means that this is the magnitude of the electric field of this as when this is at 8 centimeters. Right, this is, right? Because when this is at 8 centimeters, that's where this is 0. So that means that this is equal in magnitude when it's here to this one that's being caused from that distance there. All right. So that allows me then to set up this equation. KQ1 over D equals KQ2 over 0.08. All right. And now this value is the asymptote. So this is, and then what am I doing? I'm solving for Q2 in terms of Q1, right? Or no, in terms of, I'm just solving for that. Because this value, this is the 5.76 times 10 to the negative 7th. I'll multiply this by 0.08. The k's cancel out. Oh, no, they don't, because this k is included in here, so I still have to divide by this k. So this is 9 times 10 to the 9th. And this turns out to be 5.12 times 10 to the negative 18th coulombs, right? So our final answer is negative 5.12 times 10 to the negative 18th coulombs. All I did was I solved for this. And this whole thing is that value. And now I want to know how much is this in terms of E, right? And so I've got this negative 5.12 times 10 to the negative 18th. And for every 1 electron, I have negative 1.6 times 10 to the negative 19th. And that comes out to 32 electrons. And that's it.